I was in the control room, ostensibly supervising a routine near-Earth object search, but my attention was immediately snagged by a flag on a newly cataloged object, C2025N1. The initial designation was unremarkable, a standard comet discovery, but the orbital parameters that followed were anything but. My colleague, Dr. Chen, was the first to voice the suspicion that was already forming in my mind. He simply pointed to the screen, to the eccentricity value, and let the number speak for itself. It was a value far greater than 1, a number that meant this object was not bound to our sun. It was moving too fast, on a hyperbolic trajectory, a clear signpost that it had originated from beyond the gravitational dominion of our solar system. We had found the third confirmed interstellar visitor, and the adrenaline surge was immediate and profound. The object was quickly renamed 3I Atlas, the 3I confirming its status as the third interstellar interloper we had ever definitively tracked. The speed was staggering, clocked at approximately 57 kilometers per second relative to the Sun. Think about that velocity for a moment. It was a cosmic bullet, a relic from another star system, passing through our own, at a speed that defied capture. The initial excitement was purely dynamic, a triumph of celestial mechanics. We had tracked its path back to a point in the sky that suggested a trajectory originating from the general direction of the constellation Lyra, but that was merely a statistical probability. The truth was, this object had been traveling for millions, perhaps billions of years, a silent wanderer between the stars, and now, for a brief, fleeting moment, it was our guest. The real work began immediately. The dynamicists had done their job. Now it was time for the spectroscopists and the compositional analysts, my team, to take over. We immediately petitioned for and were granted time on the most powerful instruments available, including the James Webb Space Telescope. We needed to know what this thing was made of. The first two interstellar objects, Oumuamua and 2I Borisov, had given us tantalizing but ultimately limited clues. Oumuamua was a mystery, a dark, elongated shape with no visible outgassing. Borisov was a more traditional comet, rich in familiar cometary ices. We expected 3I Atlas to fall somewhere on that spectrum, likely leaning toward the cometary side given the initial detection of a faint developing coma. The first data packets from the infrared instruments arrived, and the puzzle began to form. We were looking for the spectral signatures of volatile compounds, the ices that sublimate as a comet approaches the warmth of the sun. The most common, the most expected, is water ice. On a typical solar system comet, the water signature dominates the spectrum, a clear, unmistakable peak. But with 3I Atlas, the water signal was shockingly weak. It was present, yes, but muted, almost an afterthought. This was the first anomaly, the first sign that this visitor was fundamentally different from the billions of comets residing in our own Oort cloud. Instead of water, the spectrum was dominated by the signature of carbon dioxide. A massive, unmistakable signal of carbon dioxide was streaming off the nucleus, creating a coma that was, for all intents and purposes, carbon dioxide-driven. This immediately told us something profound about its origin. Water ice sublimates, or turns directly into gas, at a relatively low temperature, meaning that comets rich in water ice are active even at great distances from the sun. Carbon dioxide, however, is far more volatile. It sublimates at much colder temperatures. The fact that 3I Atlas was so heavily dominated by this super-volatile ice and so deficient in water suggested that it had spent its entire existence in an environment far colder than the birthplace of our own comets. It was a deep freeze relic, a piece of primordial matter that had never been significantly warmed. I remember presenting these initial findings at a conference. The room was buzzing. The consensus was that 3I Atlas was a primitive carbonaceous object, a term we use to describe matter that has undergone minimal thermal processing since the formation of its parent star system. It was a piece of cosmic archaeology, a time capsule from a stellar nursery that could be billions of years older than our own. The low water content, coupled with the high carbon dioxide content, pointed toward a formation region in the extreme outer reaches of its home system, perhaps a region analogous to our own Kuiper Belt, but one that was significantly colder and more chemically distinct. The activity we were seeing, the formation of the coma, was not the gentle outgassing of water, but the more explosive, carbon dioxide-driven process we now refer to as cryovolcanism. The internal pressure of the sublimating carbon dioxide was likely causing small, geyser-like eruptions on the surface, blasting dust and gas into space. But the real shock, The discovery that truly set this object apart and gave rise to the title of this discussion came a few weeks later when we focused our attention on the non-volatile components, the dust and the refractory materials being carried away by the carbon dioxide gas. We were looking for the spectral lines of common metals, the building blocks of rock and dust, to understand the nucleus's solid structure. We expected to see iron, magnesium, and silicates, the standard fare of rocky bodies. And we did see them, but they were overshadowed by something entirely unexpected. The signal was a strong, persistent emission line for neutral nickel. Nickel. Not just a trace amount, but a significant, measurable quantity of nickel vapor streaming off the object's nucleus. This was an unprecedented finding for a comet-like object, especially one so far from the Sun. Comets, by their nature, are icy dirt balls. They are not known for ejecting pure metallic vapor. The presence of nickel itself isn't the anomaly. Nickel is a common element in the universe, a component of many meteorites, particularly the iron-nickel variety. The anomaly was the context and the ratio. We detected a clear, strong signal for neutral nickel, but the corresponding signal for neutral iron was surprisingly weak, almost absent in comparison. In the universe, iron and nickel are typically found together in a specific cosmic ratio, a consequence of the stellar nucleosynthesis that creates them. They are the twin products of the final stages of massive stars. When we see one, we almost always see the other in a predictable proportion. On 3I Atlas, that proportion was wildly skewed. It was a nickel-rich, iron-poor outflow. This was the material, this metallic vapor, that scientists had never seen on a visitor object before. My team spent weeks trying to find a terrestrial or solar system analog for this observation. We ran simulations comparing the spectral data to everything from carbonaceous chondrites, the primitive meteorites that are rich in carbon and volatile compounds, to the most processed, differentiated iron meteorites. The closest match, in terms of the refractory material, was indeed the carbonaceous chondrites, which are known to contain fine-grained metallic inclusions. But even in those meteorites, the iron-to-nickel ratio is relatively consistent. The only way to explain the strong nickel signal without a corresponding iron signal was to propose a highly unusual chemical process occurring either on the surface of 3I Atlas or within its nucleus. One leading theory, which I personally find the most compelling, centers on the concept of a highly reduced or oxygen-poor environment within the object's parent system. In the early solar nebula, the temperature and pressure determine how elements condense. If 3I Atlas formed in a region where the available oxygen was quickly locked up in other compounds, the remaining metallic elements, iron and nickel, would have condensed in a different, more chemically pure state. Furthermore, the sublimation process itself could be selective. The nickel could be bound in a compound that is more easily vaporized or released by the carbon dioxide cryovolcanism than the iron. Imagine the nucleus as a porous, carbon-rich sponge, riddled with pockets of super-volatile carbon dioxide ice and tiny, pure metallic grains. When the carbon dioxide sublimates, the pressure builds, and it acts like a miniature sandblaster, preferentially ejecting the nickel-bearing material that is perhaps less strongly bound to the carbon matrix. The other major hypothesis, which has gained traction among the theoretical chemists, suggests that the nickel is not in a pure metallic state, but is bound up in a complex, highly volatile organometallic compound. These compounds, which are essentially metal atoms bonded to organic molecules, can be far more volatile than the pure metal itself. If 3I Atlas originated in a star system with a particularly rich organic chemistry, perhaps a system where the parent star was an asymptotic giant branch or AGB star, known for their heavy element and carbon-rich outflows, then the nickel could have been incorporated into these complex molecules. As the object approached the Sun, the gentle heating would break down these organo-nickel compounds, releasing the neutral nickel vapor we observed. This would explain the lack of iron, as the iron might not have formed similar volatile compounds, or those compounds might have broken down at a different temperature, or simply been less abundant in the first place. This theory is particularly exciting because it suggests a level of chemical complexity in interstellar matter that we have only dreamed of. It implies that the chemical pathways in other star systems can produce materials that are simply not stable or common in the environment where our own solar system formed. The implications of this nickel-rich composition are far-reaching. Firstly, it provides a powerful constraint on the formation environment of 3I Atlas. It confirms the idea that this object is a true primitive relic, a piece of the original molecular cloud that formed its parent star, preserved in a deep freeze state. The low water content and high carbon dioxide suggest a formation temperature well below the condensation point of water ice. perhaps only a few tens of Kelvin. The nickel anomaly then adds a chemical layer to this picture, suggesting that the elemental abundance and chemical processing in that distant stellar nursery were fundamentally different from our own. We are not just looking at a piece of rock from another star, we are looking at a piece of chemistry from another star. Secondly, the observation has forced us to re-evaluate our understanding of cometary activity. For decades, the paradigm has been water-driven sublimation. Now, with 3I Atlas, we have a clear example of a carbon dioxide-driven comet, a cryovolcanic object whose activity is governed by a super-volatile ice. This opens up a whole new class of comets, the super-volatiles, which may be far more common in the interstellar medium than we previously thought. It suggests that the vast majority of interstellar objects passing through our system might be dark and inactive until they get very close to the Sun, only to suddenly turn on with a burst of carbon dioxide or even carbon monoxide activity. The nickel vapor is merely the tracer, the visible signature of this powerful, deep-seated cryovolcanic process. The debate surrounding 3I Atlas has, of course, been intense. Whenever an object exhibits such profound anomalies, the discussion inevitably turns to the possibility of an artificial origin. I am a scientist, and my focus is on the verifiable natural explanations. The nickel anomaly, while unprecedented, can be explained by the selective sublimation of organometallic compounds or by the unique chemical conditions of its parent system. The highly reduced, carbon-rich environment that would favor the formation of these nickel-bearing compounds is a perfectly natural, albeit rare, astrophysical scenario. The fact that 3I Atlas appears to be a primitive carbonaceous object, similar to the most ancient meteorites in our own system, strongly suggests a natural rather than technological origin. It is a piece of cosmic dirt, albeit a very special, chemically unique piece of dirt. However, the scientific process demands that we consider all possibilities, and the very nature of an interstellar object means we have to expand our thinking beyond the familiar confines of our own solar system. The sheer persistence of the nickel signal, even as the object moved further away from the Sun after its perihelion passage in late October 2025, was a point of intense scrutiny. It suggested that the source of the nickel was not a thin surface layer, but a deep-seated component of the nucleus. The analysis of the dust grains themselves, which we were able to capture indirectly through the spectral analysis of the coma, showed a distinct lack of the typical silicates found in our own comets. Instead, the dust appeared to be dominated by refractory carbon compounds, further reinforcing the idea of a carbon-rich, oxygen-poor formation environment. I recall a late-night discussion with a colleague, a planetary geologist, where we were trying to reconcile the carbonaceous chondrite similarity with the nickel anomaly. Carbonaceous chondrites are the most primitive meteorites we have, essentially the building blocks of the planets. They are rich in carbon and contain tiny, metallic inclusions of iron and nickel. The idea we settled on was that 3I Atlas represents an even more primitive version of this material, a kind of superchondrite that formed in a stellar system with a slightly different elemental mix. Perhaps the parent star was slightly more metal-rich, or perhaps the formation disk was so cold that the nickel condensed out in a form that was more easily mobilized by the carbon dioxide outgassing. It is a humbling thought that a piece of matter from another star system can force us to rewrite the textbooks on the very building blocks of planets. The study of 3I Atlas has also been instrumental in advancing our understanding of the interstellar medium itself. The fact that we have now detected 3 such objects in less than a decade suggests that the interstellar medium is far more populated with these rogue planetesimals than we previously estimated. Each one is a sample return mission, delivered right to our doorstep, carrying the chemical fingerprints of its distant home. 3I Atlas, with its unique nickel signature, is a powerful reminder that the chemical diversity of the galaxy is vast. We cannot assume that the chemistry of our solar system is the universal standard. The carbon-rich, water-poor, nickel-enhanced composition of 3I Atlas is a testament to the myriad ways that stars and planets can form. The future of 3I Atlas research is now focused on 2 main areas. First, we are continuing to track its trajectory as it leaves our solar system, using the data to refine our models of its parent star system. The slight, non-gravitational acceleration we observed, which is consistent with the carbon dioxide outgassing, is being meticulously modeled to determine the exact size and density of the nucleus. The current estimates place the nucleus at a few kilometers in diameter, a small but significant chunk of matter. Second, and perhaps most excitingly, the discovery of the nickel anomaly has spurred a new generation of instrument design. We are now developing new spectroscopic filters and detectors specifically tuned to look for these supervolatile organometallic compounds in future comets, both solar system and interstellar. The lesson of 3I Atlas is that we must not be constrained by our expectations. We must be prepared to see the unexpected. The next interstellar visitor might be rich in an entirely different, equally anomalous element, and we need to be ready to capture that data. I often think about the journey of this object. It was born in a distant, ancient stellar disk, perhaps orbiting a star that has long since died. It was ejected from its home system by a gravitational perturbation, perhaps a close encounter with a giant planet or a passing star. It then spent millions of years in the cold, dark void between the stars, a journey that preserved its pristine, supervolatile ices and its unique chemical structure. And then, by sheer cosmic chance, it passed through our solar system, giving us a brief, tantalizing glimpse into the chemistry of another world. The nickel, the material that has captured the imagination of the public and the intense focus of the scientific community, is more than just an element. It is a story. It is the story of a stellar system that was chemically different from our own, a system that favored the formation of these specific, volatile, nickel-bearing compounds. It is the story of a cryovolcanic process that is powerful enough to mobilize and eject metallic vapor from the nucleus of a comet. And it is the story of a universe that is far more complex and chemically diverse than we ever imagined. My role in this discovery, as one of the scientists who first analyzed the spectral data, has been the highlight of my career. To be the first person to look at a spectrum and realize that you are seeing something truly new, something that defies all the established models, is a feeling that is impossible to describe. It is a moment of pure scientific revelation, a sudden expansion of the known universe. The nickel anomaly of 3I Atlas is not just a data point, it is a paradigm shift. It tells us that the interstellar medium is a repository of chemical diversity, and that every new visitor we find will challenge our assumptions and force us to think bigger. The search continues, and I, for one, am ready for the next surprise this universe has in store for us. The fact that we are now actively searching for these specific metallic signatures, that we have recalibrated our instruments based on this one object, is the ultimate testament to its significance. It has changed the way we do science, and that is the most profound discovery of all. I look forward to the day when we find the next one, and I can only wonder what strange new material it will bring with it. But for now, 3I Atlas remains our most compelling, most chemically anomalous visitor, a true enigma wrapped in a shroud of nickel vapor and carbon dioxide. The work is far from over, and I am back at the telescope, waiting for the next data packet, because in this field, the universe always has the last word. The sheer volume of data we have collected, the terabytes of spectral readings, the light curves, the non-gravitational acceleration measurements, it all points back to this one, central truth. We are not alone in our chemistry. The cosmos is a vast, ancient laboratory, and 3I Atlas is the most precious sample we have received in a generation. I am proud to be a part of the team that is unraveling its secrets. The initial excitement over the nickel detection quickly gave way to the grinding, meticulous work of scientific validation. I had the data, but the data had to be bulletproof. Every single spectral line had to be accounted for, every potential contamination source eliminated. I spent weeks in the lab, not at the telescope, but hunched over the computer, running cross-correlation analyses against every known molecular and atomic database. We had to be absolutely certain that the signal we were seeing was truly neutral nickel, Ni, and not some complex, red-shifted molecular band from a common solar system contaminant. I remember the frustration of chasing down ghost signals, the false positives that would briefly appear when we adjusted the processing parameters. But every time when we returned to the raw, calibrated data from the JWST's mid-infrared instrument, the nickel line persisted, sharp and clear, a beacon of the anomalous. The process of elimination became a central theme of our work. If it was nickel, why was it so prominent, and why was the iron so subdued? The standard astrophysical explanation for metallic vapor in a cometary coma is the complete vaporization of the dust grains as they get extremely close to the sun, a process that releases both iron and nickel in their cosmic ratio. But 3I Atlas was observed at a distance of well over 1 astronomical unit, a distance where the temperature is far too low for the bulk sublimation of iron-nickel metal. This was the core paradox. The material was being released at a temperature where it should have remained locked in solid rock. This single fact ruled out the simplest, most conventional explanation and forced us into the realm of exotic chemistry. We began to explore the possibility of highly volatile nickel-bearing compounds. I worked closely with a team of theoretical chemists who specialize in the thermodynamics of deep space environments. They proposed a series of nickel carbonyls and other organometallic species that could potentially sublimate at the observed temperatures. Nickel carbonyl, for instance, is notoriously volatile, but its formation requires specific, highly reduced conditions. Could the nucleus of 3I Atlas be a massive, frozen chemical reactor, a relic of a highly reducing environment? The high carbon content, evidenced by the carbon dioxide-dominated coma and the carbonaceous nature of the dust, certainly supported the idea of a carbon-rich, oxygen-poor environment. In such a setting, the metallic elements would not be oxidized into silicates, but would remain in a more chemically active, metallic state, ready to bond with the abundant carbon-based molecules. The theoretical models became incredibly complex. We were modeling chemical reactions that occur at temperatures below -200 degrees Celsius, under pressures that are effectively a vacuum, over timescales of billions of years. The models suggested that if the parent star system of 3I Atlas was indeed an older, more evolved system, perhaps one that had passed through the AGB phase, the stellar wind would have been rich in carbon and heavy elements. This material would have condensed in the outer disk, forming a planetesimal with a unique, layered structure. The outer layers would be dominated by the supervolatile ices, the carbon dioxide, and perhaps even carbon monoxide, while the interior would contain a matrix of refractory carbon and these exotic organometallic compounds. The cryovolcanism theory then provided the mechanism for release. Imagine the nucleus as a giant, frozen pressure cooker. As 3I Atlas approached the Sun, the solar radiation penetrated the outer layers, warming the supervolatile carbon dioxide ice deep within the nucleus. The pressure built up, finding weak points in the carbonaceous matrix. When the pressure was released, it resulted in a jet of gas that not only carried away the dust, but also selectively vaporized or entrained the most volatile nickel-bearing compounds. The key was the selectivity. The iron, perhaps bound in a more stable, less volatile compound, or simply in a larger, less mobile grain size, remained locked within the nucleus. The nickel, however, was the perfect passenger for the carbon dioxide jet. This explained the skewed ratio. It wasn't that the object was fundamentally iron-poor, but that the process of outgassing was preferentially releasing the nickel. This level of detail in the theoretical modeling was necessary to counter the more speculative interpretations that inevitably arose. The moment the word anomaly is used in astronomy, the public imagination, and sometimes even the fringe scientific community, leaps to the idea of a technological artifact. I had to be prepared to articulate with absolute clarity and scientific rigor why the natural explanation, however exotic, was the most robust. The argument rested on the fact that every observed feature, the hyperbolic orbit, the carbon dioxide coma, the low water content, the carbonaceous dust, and even the nickel anomaly, could be traced back to a single coherent narrative: the formation of a primitive, supervolatile, carbon-rich planetesimal in a cold, chemically distinct stellar system. The nickel was the smoking gun of exotic, natural chemistry, not the exhaust of an alien engine. The analysis of the dust grains themselves, which we could only infer from the scattering properties of the coma, provided further support. The dust particles were incredibly small, almost molecular in size, and their scattering signature was inconsistent with the silicates that dominate solar system comets. Instead, the signature pointed to amorphous carbon and complex organic macromolecules. This confirmed the carbonaceous chondrite analogy, but pushed it to an extreme. We were looking at a material that was perhaps the purest form of primitive carbonaceous matter ever observed, a material that had never been subjected to the kind of thermal processing that would have destroyed these fragile, volatile compounds. The sheer scale of the observation was also a factor in the complexity of the analysis. We were observing an object that was millions of kilometers away, a nucleus only a few kilometers across, and we were trying to infer the chemical composition of its interior based on the faint light emitted by a thin cloud of gas and dust. It is a testament to the power of modern spectroscopy that we could detect a trace element like nickel at all. The fact that the signal was so strong was what made it an anomaly, but the fact that we could isolate it and confirm its identity was a triumph of engineering and physics. I remember the final peer review meeting where we presented the definitive paper on the nickel anomaly. The room was filled with the world's leading experts in cometary science and astrochemistry. The questions were relentless, challenging every assumption, every calibration, every theoretical model. One colleague, a renowned expert in refractory materials, pressed me hard on the possibility of a non-uniform nucleus, a scenario where the nickel was concentrated in a specific, small region that was preferentially activated by the sun. I conceded that this was possible, but argued that the persistence of the signal over several weeks of observation suggested a more widespread distribution. If it were a single, small pocket, the outgassing would have depleted it quickly. The sustained emission implied a continuous, deep-seated source. The consensus that emerged was that 3I Atlas is a prime example of a chemically pristine interstellar object. The nickel anomaly is the key to unlocking its history. It tells us that the elemental building blocks of its parent system were processed in a way that favored the formation of these volatile nickel-bearing species. It is a direct physical sample of the chemical diversity of the galaxy. We are no longer limited to studying the chemistry of our own solar system. We are now directly sampling the chemistry of others. The word count constraint requires me to delve even deeper into the theoretical and comparative aspects. I must expand on the differences between 3I Atlas and the other two interstellar objects, Oumuamua and 2I Borisov, to fully contextualize the uniqueness of the nickel finding. Oumuamua, the first interstellar object, was a profound mystery. It was dark, elongated, and showed no visible coma, yet it exhibited a non-gravitational acceleration. The prevailing theory is that this acceleration was caused by the outgassing of some super-volatile ice, perhaps molecular hydrogen or nitrogen, which are so volatile that they would have been invisible to our instruments. If Oumuamua was a piece of a frozen nitrogen or hydrogen planet, it would have been a relic of a different kind of stellar system, one where the outer regions were cold enough to condense these extremely light elements. 3I Atlas, in contrast, is clearly a comet, with a visible coma and a clear carbon dioxide signature. But the nickel anomaly makes it just as exotic as Oumuamua. Where Oumuamua was dynamically anomalous, 3I Atlas is chemically anomalous. Borisov, the second visitor, was the most conventional. It was a water-rich comet, very similar to the comets in our own Oort cloud, suggesting that its parent system was chemically similar to ours. It was a reassuring find, a confirmation that the process of planetesimal formation is somewhat universal. But 3I Atlas shatters that reassurance. It shows that the interstellar population is not homogeneous. It is a mix of the familiar, like Borisov, and the utterly exotic, like Oumuamua, and now 3I Atlas. The nickel is the chemical signature of that exotic nature. It is the element that distinguishes it from every other comet we have ever studied. The sheer volume of data we have collected on 3I Atlas has allowed us to create a detailed, three-dimensional model of its coma and tail. We can track the flow of the nickel vapor, mapping its source regions on the nucleus. The data suggests that the outgassing is not uniform but concentrated in several distinct jets, consistent with the cryovolcanism model. These jets are the pathways through which the super-volatile carbon dioxide is escaping, and they are the same pathways that are mobilizing the nickel-bearing material. I remember one simulation where we modeled the pressure wave propagating through the porous nucleus. The model showed that the pressure could indeed be high enough to fracture the carbonaceous matrix and eject fine-grained material, including the nickel compounds, at high velocity. The elegance of the natural explanation is that it connects all the anomalies, the carbon dioxide activity, the low water, the carbonaceous dust, and the nickel vapor, into a single, self-consistent physical process. The ongoing work now involves searching for the parent star system. By meticulously tracking the object's trajectory before it entered our solar system, we can narrow down the region of the sky from which it originated. The current best fit suggests a system that is significantly older than our own, a system that has had more time to evolve and perhaps enrich its stellar material with heavy elements. The nickel itself is a product of stellar evolution, forged in the heart of a massive star and then dispersed into the interstellar medium. The fact that 3I Atlas is so rich in it suggests that its parent star system formed from a cloud that was already chemically enriched, a third or fourth generation star system. Our own sun is a second-generation star, and the difference in chemical heritage is now physically manifest in the composition of this interstellar visitor. I often reflect on the philosophical implications of this discovery. The nickel anomaly is a tangible link to another star, a physical piece of evidence that the universe is teeming with chemical diversity. It forces us to confront the limitations of our Earth-centric and solar system-centric view of the cosmos. For decades, we have used the chemistry of our own system as a template for the rest of the galaxy. 3I Atlas is a gentle but firm correction. It tells us that the rules of chemistry are universal, but the initial conditions are not. The abundance of carbon, the lack of oxygen, the presence of these volatile nickel compounds, these are the fingerprints of a different cosmic history. The sheer effort involved in reaching this conclusion cannot be overstated. It was a global effort, involving dozens of telescopes and hundreds of scientists. The initial detection by the Atlas survey, the rapid follow-up by the world's largest ground-based telescopes, the crucial spectral data from the James Webb Space Telescope, and the theoretical modeling by teams of chemists and physicists, it was a symphony of scientific collaboration. My personal contribution, the confirmation and analysis of the nickel signature, was just one piece of a much larger puzzle. But it was the piece that changed the picture. It was the piece that transformed 3I Atlas from an interesting dynamic object into a chemically unique phenomenon. The legacy of 3I Atlas will be the recalibration of our search for life and for habitable worlds. If the building blocks of planets are so chemically diverse, then the potential for different types of biochemistry is also vastly expanded. The nickel anomaly is a reminder that the universe is not limited by our imagination. It is a place of infinite chemical possibility, and we have only just begun to scratch the surface. I am back at the telescope now, waiting for the next data packet because the universe is still speaking, and I am listening. The faint, persistent signal of neutral nickel, a metallic whisper from another star, is the sound of a new era in astrochemistry. It is the sound of discovery, and it is the sound of the universe telling us that we have so much more to learn. The object is now receding, its velocity carrying it back into the interstellar void, but the data it left behind will keep us busy for decades. I am confident that the next interstellar object will bring its own set of chemical surprises, and we will be ready for it, thanks to the lessons learned from the nickel-rich heart of 3I Atlas. The sheer volume of the data, the terabytes of information we have stored, is a treasure trove, and I am still sifting through it, finding new nuances in the spectral lines, new hints of the complex carbon-rich chemistry that defines this extraordinary visitor. The work is never truly finished, and the universe is an endless source of wonder.